Electromagnetism is the invisible scaffolding of the modern world. In your AS level studies, you looked at static electric fields and simple circuits. Now we bridge the gap. You will discover that electricity and magnetism are two sides of the same coin. Moving charges create magnetic fields, and external magnetic fields exert forces on moving charges. We are moving from flat, one-dimensional circuits into three-dimensional vector space. We begin with the magnetic fields due to current. How do moving charges warp the space around them? You will learn to sketch the precise magnetic field patterns generated by long, straight wires and solenoids. You will master the right-hand grip rule to determine field directions and understand exactly why a current-carrying coil behaves just like a bar magnet. This is the foundation for everything that follows. Once you can map a field, we look at what it does. Topic 2 is the force on a current-carrying conductor. This is the macroscopic push that makes electric motors and loudspeakers work. To calculate this kick, we first define magnetic flux density, measured in Tesla. Cambridge examiners love this definition. It is the force acting per unit current per unit length on a straight wire placed at right angles to the magnetic field. With that defined, you will use the equation F equals BIL sine theta to calculate the force on any wire. You will also use Fleming's left-hand rule to predict the exact direction of that force in 3 dimensions. Do not mix up your hands here. Topic 3 zooms in. We move from a whole wire to the force on a moving charge. How does a magnetic field alter the microscopic path of a single moving particle? You will use F equals BQV sine theta to find the force. Because this force is always perpendicular to the velocity, it acts as a centripetal force. The magnetic field can change the direction of the particle, forcing it into a circular orbit, but it does zero work, so the speed never changes. Finally, we reach the Hall effect. This is a brilliant, highly examined application of everything you have learned. When an external magnetic field deflects electrons inside a solid conductor, they build up on one side, creating a transverse voltage. You will derive the equation for this Hall voltage from first principles and see how a simple slice of semiconductor can be used as a probe to measure invisible magnetic fields in the laboratory. This unit is heavily examined in Paper 4, demanding clear 3D visualization and step-by-step logical arguments. By the end of this unit, you will be able to map magnetic fields, calculate forces on wires and single charges, analyze circular particle orbits, and derive the Hall voltage. You are ready to begin.